All of these decay equations are things that you should be able to predict the products of, knowing the type of decay, by looking at conservation of nucleons, which is the top number, and conservation of charge, which is the bottom number. You need to know the nuclear structure, I suppose, is the way to describe it, of an alpha particle. It's a 4-2 notation, which means there's 2 protons and 2 neutrons. You need to know the nuclear notation for a beta particle. It's 0, -1 beta, or 0, -1. You could use E for electron. The negative in the beta or the negative in the electron is not a number of protons, it's simply a charge. You also need to know that the beta decay is always accompanied by this antineutrino that you see on the right. Be careful in predicting the number of protons or the atomic number of the daughter material. We call the thing you start off with the parent, and what you end up with the daughter material. Be careful when there's negatives because it's very easy to slip up there. Gamma decay, well, this is all that happens. You have, for example, lead-207 undergoing gamma decay. Since a gamma ray photon has no nucleons and no charge, it doesn't change the content of the nucleus. It's still lead-207. What changes, though, are the arrangement of the nucleons within each nucleus. They become more efficiently put together. And for positron decay, you need to know that that is an antiparticle of an electron, or a positive beta particle, or a positive electron. Putting that positive beside the 1, I think, is very important to remind you that it's not 1 proton, it's an actual charge. And that is always accompanied by a neutrino. In all cases, I guess I'll deal with this first. With beta decay and positron decay, and also electron capture, which I'll talk about in a second, you should be able to look at the number of protons and number of neutrons, and from there determine what is actually happening. And you're expected to know, for example, then, that during beta decay, what happens is a neutron is changed into a proton, an electron, and an antineutrino, whereas in positron decay, see if I get this right without looking, in positron decay, a proton is changed to a neutron, a positron, and a neutrino. I got it. Electron capture. I'm a little torn about this because I don't have an exact percent, but I'll make one up. Like 95% of the time, if you had an electron capture problem on an exam, they would give you the details of electron capture, that an inner electron is captured by the nucleus and a neutrino is emitted. You would probably be told that, but the odd time you're not. So I don't know. I would give this to you on an exam. I would tell you in a context box what's going on here. Ian, do you have a question?
How come for the neutrino there's not 2 zeros?
I don't know. I know why. I know why I have that 0 missing, but there should be 2 zeros. Yeah. I think I have that 0 missing because I mistakenly typed antineutrino at one point and I covered it up, but I covered up the 0 as well by mistake. In all cases, if these are naturally occurring processes, and we haven't encountered a nuclear process yet that's not naturally occurring, well, we will. In all cases where there is naturally occurring process happening, which means energy is being released, it's exothermic, the mass will decrease, and the relationship between the loss of the mass and the release of the energy is that. So in all cases, you need to, if you want to find the energy change, you need to find the energy that you end up with, the mass that you end up with, the mass that you start off with, and subtract them and see where that leads you, okay? Questions? While you're looking, I just want to grab something. Take a look over your work, please. Does anybody have any questions? Okay, 12 and 13, yeah. And that's natural. This is, when I first saw this kind of question on a diploma exam, my head just about popped off. Like I recognized in general what you would have to do, but it took me a little while to sort this out. What you're asked to do for this problem is determine how much mass is lost. And in order for you to determine how much mass is lost, you really need to determine how much energy is released. That's your primary goal. Because the energy released, delta E, equals the mass lost, delta M, times c squared. So this is the loss in mass, and this is the loss in energy, which is kind of a weird way of looking at it, but the energy is lost from the nucleus and spit out somehow. And it's a very weird way of looking at it because we've already said this, the energy isn't actually in the nucleus. It comes from the creation of mass. So for that reason, I would rather just say energy released. And what that means is we need to compare the energy afterwards to any energy that there was before. But this thorium-232 nucleus is at rest. So in terms of what we would traditionally call energy, there's no kinetic energy there. There's no energy. The thorium nucleus is at rest, which is probably a lie, but it has maybe a drift velocity that's so small that it wouldn't affect anything, okay? And that means that this energy released will be the kinetic energy of the alpha particle that's spit out and the kinetic energy of the thorium nucleus after the decay happens. So the thorium nucleus is at rest, but it's going to be moving afterwards for the same reason that if I have a gun that's at rest, a rifle that's at rest, and I pull the trigger and the bullet has kinetic energy afterwards, the rifle will have kinetic energy afterwards because of a recoil velocity. And this is really a good way to think of it. This thorium nucleus that has an alpha particle in it, and that alpha particle is contributing to it being thorium, is going to spit out the thorium, and the gun is going to go backwards. The nucleus that goes backwards is like the gun. So do we have any information here where we can find these energies? Well, you're told that the energy of the alpha particle is 4.081 million eV. However, this energy has to be in joules. So let's do that first. Let's convert 4.081 million electron volts into joules so we know how much energy that alpha particle has. 4.081 multiplied by 10 to the 6 because it's millions of electron volts divided by how many joules per electron volt there are. Pardon me, multiplied by how many joules per electron volt there are. If I would have divided, I would have looked at the number that I got and recognized right away I did the wrong thing. So I'm getting 6.5296 times 10 to the negative 13 joules. And it's probably no surprise that since, we deal with large energies, but the mass changes are slight, we need to carry a lot of decimals here. So I'll just drag this on here where I can copy it. The alpha particle has 6.5296 times 10 to the negative 13 joules of energy. This is a beast of a question. It really illustrates Alberta Ed's philosophy that these two physics principle questions are ones that very few students overall usually get. And this is one that I would agree wholeheartedly with. I wouldn't be surprised if you see this on a diploma exam and only a third of you or a quarter of you get this. It's a complicated question. So now, how do we find the kinetic energy of the nucleus after? Well, we would have to know the speed after. Because we know the mass, you're told the mass of the nucleus. You're not told what it is, and I don't know that we need to find it, but you're told the daughter nucleus is this number for a mass. That means after the alpha particle is emitted, that's the mass that's left over there. Okay? Well, how would you find how fast the rifle moves backwards? You would use conservation of momentum. You would say that the momentum before and the momentum after must be equal. And you would say the rifle being held in steady hands with the bullet loaded in the cartridge has no momentum, and then you would say we're going to have to take the momentum of the bullet afterwards, which in this case is the alpha particle, and the momentum of the rifle afterwards, in this case, which is, I'm going to do some abbreviation here just because I crowded myself out, daughter nucleus. Okay. And this, to make sure you're following my thinking here, this is what we need to put here. But it's like now you're being poked with a sharp stick, because you also have to figure out the speed of the alpha particle before you can do the conservation of momentum. Like it seems to never end. So it's why, like I said, when I read this question, my head nearly popped off. Like I realized how much work it's going to be. So I'm going to take this energy and multiply by 2 and divide by the mass of the alpha particle. Now, I've mentioned to you in nuclear physics applications, you use numbers that are given to you, but if you're not given, say, an alpha particle mass, use the one on your formula sheet. Okay? And what I'm doing is I'm setting this equal to a half mv squared so that I can find the speed. So now I know how fast the alpha particle is moving. And again, I'm just going to dump this here. 1.401 something times 10 to the, I think that is 7 meters per second. Okay. So now I have to take 0 equals the mass of the alpha particle times the speed of the alpha particle plus the mass of the daughter nucleus times the speed of the daughter nucleus. And we know the mass and the speed of the alpha particle, and we know the mass of the daughter nucleus, so now we can find the speed of the daughter nucleus. I hope you recognize, Annalee, when we rearrange this equation for v of the daughter nucleus, we will get a negative number because it's a recoil velocity, and this is actually about vectors on the left, but we're not going to worry about putting it in here. So I'm going to take this speed times the mass of the alpha particle. That's the momentum of the alpha particle. I would have to subtract it to the other side before I divide by the mass of the nucleus, which would make it negative, although probably many of you won't really worry about that because you're not going to use the negative later anyway. And now we need to divide by the mass of that nucleus, which was 3.785316 multiplied by 10 to the negative 25, and I get a recoil velocity of that number, and the negative means in the opposite direction. So I can drop the negative. This is how fast it's moving. We are doing this, all of this, so that we can determine the energy of the nucleus afterwards, the kinetic energy, because these two energies added together represent the loss of energy, which we can use to find the loss of mass. So we still now have to take 1/2 mv squared of this number. 0.5 times the mass of this nucleus is 3.785316 multiplied by 10 to the negative 25 times the speed squared. And, you know, let's face it, There are underlying physics ideas here that make this complicated, but I think what makes it most complicated is there's so many things. It's a difficult problem. Want to make sure that I've entered that right. 3.785316 times 10 to the negative 25 times the speed squared times 0.5. This is the kinetic energy of the nucleus after the alpha particle is emitted. I need to add to that the kinetic energy of the alpha particle after the alpha particle is emitted. And I think, is this rounded? Oh no, I have it up here anyway, I think. I want to carry all my decimals. Yeah, there it is. I need to add the kinetic energy of the alpha particle and I get that energy released. However, looking just to the right of my calculator screen, the energy released is equal to the loss in mass times the speed of light squared. So if I divide by the speed of light squared, I get 7.38 times 10 to the negative 30 kilograms, and I see some people nodding, so that's the right answer. I don't know, I'm just being brutally honest here, I don't know what Alberta Ed was thinking when they put in a question like this on the exam. I have a belief that when they field tested the rest of the exam questions, the average came in really high, and they thought, well, let's throw in something there because we don't like that high average. We want it to be a certain level. And sometimes they do that. They want a provincial average of 68.2 or whatever they're designing it for. I hope you appreciate me being honest with you here and saying part of me every time I teach this unit says, don't even do this. But then part of me says there are going to be students, the ones that strive for like 100%, who are going to be upset if they see this on an exam and they've never seen anything like it in class. Okay. We're going to move on now and take a look at half-life. By the way, no, sorry, physics principles. Well, man, there were shovelfuls of physics we were doing here, but you did use conservation of momentum at some point, and you did use conservation of mass energy. You never use conservation of energy in nuclear changes. It's conservation of mass energy. All right. That was okay, Annalie? Okay. So we're looking here at lesson 4.8, which is radioactive decay and half-life. If you're in 30-1 right now, or you have completed 30-1, and there's, I think, at least one person who has, we've done these types of problems in Math 30. We're going to be interpreting half-life graphs for radioactive decay and using the half-life formula to solve radioactive decay problems. When you have alpha, beta, and gamma decay happening, you have a lump of radioactive material, and some of the nuclei may remain the same for years, and then all of a sudden, out of nowhere, an alpha particle comes out. I mean, a perfect illustration here is if I take, this is a beta source, right? And I don't know what the year on this is. I don't even know if there is a year there. Do you see a year on there, Annalie?
January 2016.
2016. So this was manufactured in 2016, a little bit over 6 years ago. And every time you hear that click, beta particles are being emitted, so the nuclei are changing. And we could write the nuclear decay equation to find out what they're changing to. But, you know, I come back a time later and there's more beta particles being emitted. So if I come back 6 years from now, it's still going to be ticking, which means that some of the nuclei that are not decayed now won't decay for another 6 years, or another 10 years, or another 40 years. And the question here is, what determines whether a particular nucleus decays or not? And the answer is, it's a probabilistic model. It's statistics. It turns out that there are statistical laws in physics. There are laws that say things are going to happen and we can't predict which one is going to happen, which individual task is going to happen, but we can predict what the whole cloud of things is going to do. It's like the weather. Weather prediction has gotten amazingly accurate over the years, but it can't predict how fast an individual molecule in the air is moving, but it can predict the temperature of the entire air mass quite accurately. And it turns out that over a given period of time, the probability of a nucleus decaying is always 50%, 0.5. This is just like tossing coins. So, except that a toss of a coin is an event that happens and then it happens again. Decay is something that happens gradually over time. It isn't happening periodically. It's always happening. So the given period of time for each nucleus to either decay or not is called the half-life. What does that mean? It means if the half-life is 10 years, every nucleus has a 50% chance of decaying in 10 years somewhere. Some of them will decay right away. Some of them will decay later on in the 10-year period. Some of them will not decay at all. But at the end of the 10 years, half of them will have decayed. That's what this model is saying. And I say model as if it's some kind of weird prediction. It's true. If during one half-life the probability of each nucleus decaying is a half, or 50%, then you would expect half of them to decay during that time. Now, just a second here. Do you agree the probability of a coin landing heads is 0.5, 50%? Does that mean if I toss 10 coins, I'm going to get 5 heads and 5 tails? No. The probabilities break down at small numbers, but that's why I'm saying it's the same as tossing a large number of coins. We can't even visualize how many nuclei there are in something. Okay? Very, very large number. So what does this mean? It means that the half-life is how long it takes for half to decay. And this type of change for you Math 30-1 people is an exponential decay, where the base of the exponential function is a half. Warm-up. Half-life of carbon-14 happens to be 5,730 years. Assume, and this is a ridiculous assumption, but let's assume we start off with 100% carbon-14. We wouldn't find that in nature, but we could procure it in a lab. You could go to a nuclear physics lab and they could manufacture some for you. And we'll talk later about how that happens. So if I say to you, what percent of the carbon-14 is still in the sample at the beginning of our experiment, it's 100%. If I look at one half-life elapsing, which is 5,730 years, and I say, well, what percent is remaining? It's going to be 50%, right? And then it's going to be 25, and then it's going to be 12.5. The percentage remaining keeps getting cut in half. And by the way, if I started off by saying 100 milligrams, then it would turn into 50 milligrams. And then it would turn into 25 milligrams. If I started off by saying 80 micrograms, then it would turn into 40 micrograms and 20 micrograms. And we need to construct now on the next page a graph. Oh, sorry, B. Compare the amount of material that decays as time goes on. If you take a look at this table, during this period of time, half, 50%, changed. During the same period of time down here, this is the same time interval, only about 3.125% was lost, which means as time goes on, less decay happens. I had a student a long time ago say, how does the sample know that there's less stuff there, so there should be less decay? And I get why you might think that way, but the reason why there are fewer decays later on is that later on there are fewer that can decay. That's the whole nature of exponential change. So we're going to construct a graph here. so that we become familiar with the graph. We start off and we say, well, at t equals 0, we have 100%. At one half-life, we have 50%. After another half-life, you have half of that, which is 25. You get the idea here. And I think really all we're really doing here is just showing this visually rather than with numbers. Half of 12.5 is the 6.25, and then the 3.125. For you math people, will this graph ever reach the x-axis? No. But this isn't math, this is physics. Will the nuclei all decay eventually? Yes. Sooner or later, and let's face it, you're not always going to have an even number that you can divide by 2. Sooner or later, you might end up with 5 nuclei that haven't decayed in that time. And if you wait another half-life, maybe only one will have decayed, or maybe none will have decayed. But, the small numbers makes it unpredictable. But sooner or later, you'll be down to 1 or 2 nuclei, and sooner or later, those 1 or 2 nuclei will decay. So what this graph looks like is that. And what is important about this graph is that the half-life is the time it takes to cut the original amount of material in half. Okay? And all isotopes that are radioactive have a particular half-life. This is the equation that we use. N equals N0 times 1/2 to the N. Those crazy guys at Alberta Ed, I don't know why they got all the N's here, but they do. N0 is an initial amount. The 0 stands for initially, t equals 0. N is the amount remaining, and little n is the number of half-lives. Okay? So, just a quick illustration of something here. I guess we'll do this first of all. In this equation, the capital N's can be grams and grams, or they can be milligrams and milligrams. They could be activity, which we'll talk about in a second. They could be percentages. They could be number of nuclei, as long as they're the same thing. Activity is the number of decays per second. So when I take a look at this needle, it's sitting around, what am I at, a scale of 1? This is good. It's sitting at around 1.4 thousand, 1.4 K. There are 1,400 of these decays happening per second. Okay. On the other hand, Mr. Blacker gave me a piece of thoriated tungsten that they use in welding. And this is emitting, which scale am I on? 100. This is emitting around 150 per second. So we would say that the activity is 150 decays per second. There's a word for that which is called becquerel. And I've already talked about this. It makes sense that if there are fewer nuclei that can decay, fewer will decay. A number of years ago, I think it was about 12 years ago, I had a medical issue and they wanted to do a nuclear blood scan, which means that they inject you with a radioactive source. They wait for it to distribute throughout the body, and then it's not a big Geiger counter, but they basically run a big Geiger counter over your whole body and find out where the radiation is. And it was an issue with my pancreas that they saw something on some images that my pancreas had some abnormalities to it, and they wanted to make sure that the blood was actually getting to the pancreas. So this is what they did. So being the geek or nerd that I am, I took a Geiger counter into the city. Okay. They phoned me in the morning and they said, "Are you going to be there for this injection and this procedure?" I said, "Yes." They phoned me a half hour later, "Are you sure you're going to be there?" And then they phoned me one more time because they're going to inject me with something which decays. And they can't put it in a cupboard and then I show up a week later and they're going to grab the stuff because it will no longer be radioactive. So they're manufacturing this stuff in the morning of my procedure. They're manufacturing it at what used to be called the Slowpoke nuclear reactor at the U of A. And it's called technetium 99M. And I got the injection at 11:30, but I waited a couple hours sitting in my car with a Geiger counter for the blood to circulate. And then I decided to start taking readings. And I breathed into the Geiger counter because I know that the lungs are organs that really have a lot of blood flowing around and diffusion happening. And it was 20,000 decays per second. And at 3:17 in the afternoon, it had dropped. And what I did was I compiled a list of data here with my Geiger counter. Got up in the morning, 7:15, read it. The next day, I just thought, well, I'll do one more. And then over 24 hours later, it was 7:50. If I want to investigate the relationship between these activities and times, I need times. I don't mean clock times. I mean hours and minutes. So from 2 o'clock to 3:17 turns out to be 1.283 hours. Okay? So I've converted these time differences into hours. And what I have is time in hours and activity in decays per second, which is called a becquerel. And I want to look at this graph. So I enter the time in list 1 and the activity in list 2. And it's not linear, is it? We know it's not going to be linear. So I don't do a linear regression. That's what it looks like. I complete an exponential regression. Don't worry about exactly what's happening here. My calculator, I've told it to find the formula that will graph this data. And when I graph the data, that's what it looks like. And then I turn my stat plot off. So this is my activity. Don't worry about the horizontal line. I found the y-intercept of that, and it's 19,854.7. The half-life is how long it takes to be reduced to half. So I divided this number by 2 and got this. And this is a good scenario that you could potentially see on an exam. So that's the half-life. And it's just a matter of finding the point of intersection, which happens to be this number. So after all of that, because I took the next day off because I just wasn't feeling that good anyway, I determined that the half-life was a little over 6 hours. And when you look up technetium 99M, that's the half-life. That's pretty, I find that really interesting, that I was able to, just with a Geiger counter, I mean, I don't want to minimize the Geiger counter. It's a valuable piece of equipment, and it reads things very accurately. But, I didn't breathe into that thing from this distance all the time. It might have been from this distance. There were lots of sources of error here. And I haven't worked out a percent error, but it's probably pretty tiny. So before we get to a couple of examples, does anybody have any questions about radioactive decay and half-life? Ian?
You mentioned on one of those substances there that there is it 1,400 decays
Per second?
per second. How do you know that if the decay is always changing?
Well, it's, I think the half-life of this, now we can talk about half-life. Can you read a half-life on there?
28.8 years.
28.8 years. So what does that mean? It means that if I turn this on, and right now at 10 o'clock on December 16th, 2022, it's 1,400 decays per second, then I have to wait 28.8 years for it to drop to 700. This time scale is very long, right? Like the graph that you're looking at that we did in our notes, the x-axis is, correct me if I'm wrong, half-lives, right? Like it says 1, 2, 3. But each of those half-lives is over 5,700 years. So yes, if I had the patience and I didn't want to do anything else in my life, I could sit here day after day, year after year, and I would see the needle on the Geiger counter start dropping. Okay. Incidentally, here are all of the alpha sources that I've bought over the years. Well, I haven't bought them, but I don't know. I can't read the dates, but there's one here from 1998. Can you read what the half-life is somewhere?
It's upside down.
Oh, sorry.
December 2009.
Not a date, though. There should be a half-life, like a number of days or something. Up here?
138.4.
138.4 days. So 138.4 days. Well, if I take, let's see, 365 divided by 138.4, well, that's good enough. 1 year is somewhere between 2 and 3 half-lives. Okay, 1998 was 24 years ago. This is how many half-lives that sample has experienced. If you take something and divide it in half 63 times, you're going to be left with nothing. I don't care. I really, if you had, I'll check it out in a second. If you had everybody on Earth flip a coin 63 times, everybody is going to end up tossing a head somewhere in there. I mean, think about it. Can you toss a fair coin 63 times, landing tails all the time? No. Sooner or later, they have all decayed. So that's why if I take any of these alpha sources and let's turn this on, first of all, recognize there's background radiation. It might tick every now and then. There's nothing on any of these. There's nothing radioactive left. But if you take a look at some of the, I'm going to go gamma, some of the gamma sources. Can you tell me what the half-life is here? It'll be in the top right corner probably.
5.27.
5.27. Can you tell me the year on that?
November 1998.
98? What's the year on this one?
2009.
98, 2009. What's the year on this one?
It's backwards. 2013.
2009? 2013. What's the year on this one?
2015.
2015. So I have a 2015, 2013, 2010,
1998.
98. So if I measure the most recent one, now I measure the next oldest one. Well, we got a problem here, and I'll tell you why that's doing that in a second. But as they get older, you're going to discover there's less and less radiation. I think one that was older was ticking more because there's more material in it. Somewhere on there it tells you how much in, called microcuries, which is a measure of the amount of material, how much is in there, and I think one of them has more. Okay. All right, let's do a few calculations. One of the things that's not on your formula sheet that you need to be able to cope with is, since this is the physics formula we use for half-life, and I like to write 0.5, and little n is the number of half-lives, you need a way to determine the number of half-lives. By the way, you Math 30-1 people, if you want to use this, P is the half-life. You got a simple equation to use. I'm not going to teach that, but in Math 30 here, but in Math 30-1, that's how we do exponential change. And I would argue that this would probably be easier. This is 0.5. A is the initial amount. T is the time. Y is the amount left. And P is the half-life. And what that means is, if you want, some of you might just want to do this. But the fact is that is lowercase n, so you need to be able to figure out how to take time and half-lives and find number of half-lives. Let's do a couple of examples. A radioactive sample of polonium-210 has a half-life of 138 days. That's this. Polonium-210, 138 days. What mass of an original 40 milligram sample will there be after 1 year? Well, n equals n0 times 0.5 to the n. N0, well, N is what we're asked to find. N0 is 40 milligrams. And then we have to put in here the number of half-lives. Well, 1 year is 365 days. Each half-life is 138 days. What I'm doing here is, I guess, using this formula that's not on your formula sheet, but I would argue that this is common sense. That, you know, you have 365 days and each half-life is 138. How many half-lives are there? I think it was that 2.6 number. Actually, we calculated it, or I calculated it up here. 2.6449. And that's it. There's nothing complicated about this formula. However, and this is not a math class, so don't think of what I'm saying as, wow, who would think that? This is not a math class. This does not mean you're going to take 40 and multiply it by 0.5 and then raise it to that number. You have to take the 0.5 raised to this first, okay? And the only reason I mention that is some of you like to do things in steps on your calculator. You don't need to, because your calculator knows. Sorry, I have to finish. I can't think and talk at the same time today for some reason. I think that looks right. Your calculator knows the order of operations. It knows it has to do the exponent first before it applies the product. 40 times 0.5 raised to the 2.644927536. So about 6.4 milligrams remain. The amount of the the amount of the parent material that's still left after that period of time is 6.4 milligrams. And by the way, I'll just show you this briefly. I mean, I really hope you understand. Bad analogy. Yeah, we'll go with this one. I really hope that you understand that if we start off, if all of these dots represent the 40 milligrams, and there's only 6.4 left, I hope you understand that it's not going to be this 6.4 that are left. It's a peppered kind of approach. So what you're going to have, I'm going to go with a long half-life, relatively speaking, is it's a random event occurring, just like people in a stadium flipping coins. Randomly, you don't know where the heads are going to be. And if you take a look here at t equals 100 seconds, of all of these nuclei, I don't know how many are there, we could work it out, there's only 52 left. However, if I reset this and I go with a small half-life, a shorter half-life, that means things are going to happen quicker, right? And after 100 seconds, I don't know that we'll have anything left. See, I want to play this again and point something out to you. We have 2 left, right? Watch that number with a short half-life over here. It goes down very predictably as there are a lot of nuclei, but then it kind of stutters. I mean, this time we have 1 left. It's a probabilistic thing. Sooner or later, that 1 nucleus will decay. Which would be more harmful? Which would give you a greater exposure to radiation? Something with a long half-life or a short half-life? Ian?
Does it depend how much material there is?
Assuming everything else is equal, that we have the same type of decay, they're both alpha decay, let's say, and we have the same amount of material.
No long half-life.
Long half-life is safer, actually. Short half-life is more, you're going to be exposed to more radiation with a short half-life because a short half-life means it's happening more frequently. So, for example, if you take a look at this short half-life, and I'm going to try to read this, so I can pause it at 50 seconds. No, bad number. I'm going to pause it at 40 seconds. I'm going to try anyway. Wow, 39 seconds. All we have remaining is 36 nuclei. So all of the blue nuclei are blue because they were red and they spit out some harmful particle. A lot of blue nuclei are there, so a lot of decay has happened. If I go with a longer half-life, I'm going to try to stop it at 40 again. This time, I have fewer blue nuclei there, fewer daughter nuclei, which means fewer decays occurred, which means in that time interval, I wasn't exposed to as many decays or as much radiation. Next question. After 1 year, what % of the original sample will be daughter material? Okay, well, we could figure this out using n equals n0. There's another way to do it, times 0.5 raised to the n, but this time put in 100%. And this will be this number 2.6449. So 100 multiplied by 0.5 raised to, in brackets, 365 divided by 128. 13.9%. That's not the answer to the question. Because that 13.9% is the percentage of the parent material remaining. These graphs are showing how much of the original isotope is still there. And what you're asked to find is what percentage of the daughter material will there be. So if this is, I'm going to say 14%, this is the parent, then the other 86% must be the daughter. 86%, of course, being the number that when added to 14 gives you 100. Did you? Okay, well, I probably entered something in correctly here. Is it 138? Okay, thank you. Let me repeat that calculation. Thank you, Annalie. %, which makes this 84%. I mean, you could certainly have done it this way. You could have said, well, out of 40, we had this much parent. We have a problem in thinking of mass, though, but that's okay. If I take 40 milligrams minus 6.4 milligrams, I get 33.6 milligrams of daughter. I mean, it doesn't quite work that way because mass is not conserved during these things, and there's alpha particles coming out as well that carry mass. But if I divide that by 40 milligrams and multiply by 100, I should get that 84%. Okay. One more question we want to look at here. In living tissue, the activity of carbon-14 is 0.23 decays per second. We could have a whole lesson on radiocarbon dating. But briefly, when you have a living organism, and you should know this from very basic science in Science 10, there's a carbon cycle that's happening. If the living organism is an animal, they are taking carbon in the form of glucose, and they are exhaling carbon in the form of carbon dioxide. If it's a plant, they're taking in carbon dioxide and they're getting rid of carbon in the form of glucose. They're producing glucose, and there's this cycle that's going on. In the atmosphere, ultraviolet radiation changes some carbon to radioactive carbon-14. Carbon-14 is radioactive. But because we're breathing in the air from the atmosphere, as long as we keep eating and breathing, the level of radioactive carbon in our system stays fixed. You would expect the decay rate to go down because it's radioactive. But it is decaying, but it's being replaced by the circle of life, okay? When an organism dies, that exchange of carbon with the environment stops, and that level of carbon-14 starts declining. Are you with me on that? So if we could measure the level of carbon-14 in everybody in the room, right now it's 0.23 decays per second. 0.23 becquerel is what we call it. In a piece of sandal, which is made from an animal, it's a leather product, analyzed by an archaeologist, they measure the decay to be 0.0018, which is less than 0.23, which makes sense because the cow devil-like in its appearance has a decay rate of 0.23 becquerel until that arrow goes through the cow. And the cow is dead. And that is going to start declining, right? It's not going to be 0.23 becquerel. So the question is, how long does it take for the activity of carbon-14 to go from an initial amount to a final amount of 0.0018 becquerel? This is the question. The spots on the cow almost look like a face. That wasn't intentional. So, what does that mean? We have n equals n0 times 0.5 to the n. So we have 0.0018 equals 0.23 times 0.5 to the n. So we have to rearrange that for n. All right. We would start by dividing both sides by 0.23. And end up with this statement that 0.5 raised to some exponent is equal to whatever that is. (0.007826). And of course, if you're in Math 30-1 right now, you know how we're going to solve this. Or if you're in 30-2, you probably know how to solve this. So bear with me because not everybody is in 30-1 right now. What you could do is take your calculator and just try 0.5 raised to the 2, 0.5 raised to the 3. You could try that, okay? But what you do instead, and you're just going to have to not worry about what this means, because it would just be more confusing than anything else, is take what's called a logarithm of both sides. And you have a logarithm key on your calculator. How many of you know what I'm talking about here? Okay. Well, what that allows you to do, and it's just the way that math works, it just works, is when you take the logarithm of something like 0.5 to the n, you are allowed to move that n out in front. It just works. Okay? So now we have this. And not to put too fine a point on it, but this is just a number. You would use your calculator to figure out what that number is. This is just a number. Which means to find n, you have to divide by that number on the left. You have to divide the number on the left by the number on the right. So we take this number, we take the log of it. You have to close the brackets on the argument. And then you divide by log of 0.5. N is 6.997. It's pretty close to 7. But that's not the answer to the question. This is half-lives we're not interested in. Well, I want to back up. You understand that the age of the sandal is how long the cow's been dead? Right? You get that idea? I mean, maybe not down to the nearest minute because, they have to tan the hide and, the sandal might not be made for years even, but it's a rough estimate here. We know that one half-life is 5730. Thank you. It's 5,730 years. So, you could set up a ratio here to find that time. You could use this formula. T over the half-life equals the number of half-lives. To me, again, a little bit of common sense goes a long way. Multiply the number of half-lives by the length of time each half-life is, and you're going to have the time. So, about 40,000 years old. And this is data from an actual discovery that was made. I was over about 25 years ago in the Swiss Alps. They found some poor guy who looked like he had been out hiking. He had a bag with some fruit and stuff, dried fruit in it. He didn't have any weapons. He looked like he was just out hiking, some very primitive clothing, and he fell in a crevasse in between two mountains. And he met his demise there. And as the ice thawed, he was discovered, so they took a sample of the sandal and they discovered that this happened about 40,000 years ago. Any questions with that example? All right. Can we use carbon-14 dating to determine the age of fossilized dinosaur bones? First of all, a dinosaur bone fossil is not a bone. The bone has long since deteriorated. What a fossil is the earth and rock being formed around the bone and condensing, and then when the bone decays and rots away, you're left with that fossil. There may be some bone material there, and let's assume there is a little bit of bone material there, and you're going to measure the carbon-14 present. Could we use carbon-14 dating to determine the age of the bone? I want to make sure you understand something first. I think everybody, because of the way North American culture is, I think everybody is aware of the Flintstones. I'm sure we have all seen an episode of the Flintstones. You are aware, cartoon notwithstanding, that it is fiction, right? That humans and dinosaurs did not coexist, that we know dinosaurs existed a very, very long time ago, millions of years ago. So why would carbon-14 not be useful? Ian? Half-life is too small. We won't have any carbon-14 left to measure over, let's just take 1 million years. 1 million years of time divided by 5,730 years for a half-life is 174, well, let's just call it 175 half-lives. I really like the coin example or illustration or analogy because the likelihood of a carbon-14 surviving 175 half-lives without decaying is just as likely as you tossing a fair coin 174 or 175 times and it always landing tails. That's like a cosmic win in a lottery system. It's not going to happen. I can tell you right now, the probability of this happening, it won't even register on my calculator, I don't think. The probability of that carbon-14 surviving is 1 in 2 to the 174. And if you actually try to calculate 2 to the 174, I don't think your calculator can cope with that. Oh, it is big. 1 in 2.39 times 10 to the 52. And 2.39 times 10 to the 52 is an unimaginably large number. Questions with I didn't actually write this down. The answer is no. Right? You would have to use some other radioisotope, something else that you could measure in the surrounding rock strata or section of the Earth. Maybe an ice sample, because there are other elements that are radioactive that get trapped in ice. Any questions with B? All right, so there are practice problems here. On Monday, we're going to be looking at fission and fusion. How many of you have heard of the big fusion discovery? Yeah, I wouldn't get too excited.